Before we get too far ahead of ourselves with this study of universal gravitation and satellite motion, maybe we should take a step back and investigate what should be an easy problem at this point. Let's see. There's the ground. Here's a 1 kilogram object, and I want to lift it to a height of 1 meter. How much work do I need to do? Or, equivalently, how much gravitational potential energy would I have stored by lifting the mass to that height? Right, I told you this would be an easy problem. The gravitational potential energy is just mgh, so this is 1 times 9.8 times 1. Now, I really mean 1 kilogram times 9.8 newtons per kilogram times 1 meter. So the kilograms cancel out. Numerically, we get an answer of 9.8, and dimensionally, we have units of newton meters, and a newton meter is a joule. Easy stuff. 9.8 joules of gravitational potential energy were stored. And if it were 2 kilograms that we lifted, it would have been 19.6 joules of energy. If it was 3 kilograms, 29.4 joules, and so on and so forth. What if instead of imagining I keep multiplying or increasing the value of the mass, what if I keep increasing the distance? What if I lift it to 2 meters? What if it's 1 kilogram, but I lift it to a height of 2 meters instead of 1 meter? Then 19.6 joules. What if I lift it to 3 meters instead? Then 29.4 joules. Now, can I say etc. on this one? Unfortunately, no. If we lift it high enough, eventually we can't discount the fact that the Earth is spherical and sits in a non-uniform gravitational field. Near the surface of the Earth, as long as we don't go to extremely high altitudes, then the gravitational field strength seems to be a constant 9.8 newtons per kilogram. But the higher up we go, the farther apart the field lines start to become, and the gravitational field drops off, and as we know, it follows an inverse squared proportionality. We need another equation to represent gravitational potential energy. Obviously, mgh isn't going to work because g isn't constant. Well, we can start with our definition of gravitational potential energy. It's equal to negative the work done by a conservative force, in this case the conservative force of gravity, and work is equal to the dot product of force and displacement. So let's assume we're going to lift something working our way outward along the radial axis. So the integral of F times dr. F dr. So our gravitational potential energy is the integral of, well, the force is G m over r squared. We have dr. Okay, so gravitational potential energy is equal to G m times the integral of r to the negative 2 dr. So gravitational potential energy is negative G m over r. The negative sign is a bit tricky. In our old definition, we always like to say that ground level, sea level, is the place where gravitational potential energy is equal to 0. After all, no two people ever agree on values of gravitational potential energy, and that doesn't matter because they'll always agree on changes in potential energy. So if I were to ask you what would be the speed of the block if we started it from a height of 1 meter and then let it go and fall back to the floor, well, regardless of whether or not you set the floor as the reference level or the release point as the reference level, you'll still find the same speed you're not going to say kinetic energy is equal to potential energy. You're going to say that the kinetic energy when it hits the floor is equal to the change in the gravitational potential energy. So knowing that we can put a reference point anywhere we want to, how about this? You might be tempted to say the surface of the Earth is the place where gravitational potential energy is equal to 0. But I have an alternative for you. Let's say that at a distance, not there, let's keep going, not there. How about when r equals infinity, that's when gravitational potential energy is equal to 0. Why should the surface of the Earth, in our universal perspective, be the special place for potential energy? It seems like the one place that's far away, if I'm infinitely far away from the surface of the Earth, I'm also infinitely far away from all other objects within our solar system. And so this becomes a more universal reference point for potential energy. Well, if the potential energy is 0 infinitely far away, as we get closer and closer to the surface of the Earth, as we fall lower and lower from that reference point, the potential energy has to become less and less. So the only explanation is that when we let gravitational potential energy equal 0 at a distance infinitely far away, then all other values of gravitational potential energy must be negative. What's the gravitational potential energy of a geosynchronous satellite with a mass of 2,000 kilograms? Gravitational potential energy is negative g/m over r. In a previous video lesson, we found that the distance from the center of the Earth to the location of a geosynchronous satellite is about 6.6 times the radius of the Earth. So if we want to answer this example question, we just need to plug in the given values. The gravitational potential energy is negative 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, multiplied by 2,000 kilograms, multiplied by 6 times 10 to the 24th kilograms, all divided by 6.6, multiplied by 6.4 times 10 to the 6th meters. Let's look at our units. Those kilograms cancel one of those kilograms. Those kilograms cancel the other kilogram. That meter cancels one of those meters, and we're left with Newton meters, which is joules, which we'd expect to get for energy. So the energy is negative. Let's see what our calculator says. So I get a value of negative 1.9 times 10 to the 10th joules. Let's take this a step farther. That's the gravitational potential energy it has when it's at the location of its orbit. So there's the Earth, capital M, there's our satellite, lowercase m, and there's a distance of 6.6 Earth radii. Well, what was the gravitational potential energy of our satellite when it was sitting at the Earth's surface? Then we have a value equal to negative 6.67 times 10 to the negative 11th times 2,000 times 6 times 10 to the 24th divided by 6.4 times 10 to the 6th. And notice, I'm not multiplying by 6.6. It's at a distance now of 1 Earth radius. So if you plug in the numerical values into your calculator, you find in this case the gravitational potential energy is a negative number of greater magnitude, meaning it's lower in value than it is at altitude, which we would expect. So we get negative 1.25 times 10 to the 11th joules. So what would be the change in gravitational potential energy to get our geosynchronous satellite from the surface of the Earth up to its altitude of orbit? So the change in gravitational potential energy would be final minus initial. So negative 1.9 times 10 to the 10th joules minus negative 1.25 times 10 to the 11th joules. That's change in gravitational potential energy of 1.06 times 10 to the 11th joules. It's a large number of joules. It's hard for me to relate to. So let me remind you of a large unit of energy called a kilowatt hour. 1 kilowatt hour is 3.6 million joules. So we could say the change in gravitational potential energy to get a 2,000 kilogram satellite into a geosynchronous orbit is equal to about 29,462 kilowatt hours. Now, if you're providing those kilowatt hours by using some sort of portable combustible fuel, it could be very expensive. I don't think they've made the electric satellite yet. I own an electric bike. I have plenty of friends who drive electric cars. I don't know of the electric satellite. But let's just make a crazy assumption that they could. When powering devices with electricity, there's a very affordable rate for electricity. It costs about 30 cents for 1 kilowatt hour. So 29,462 kilowatt hours at a rate of 30 cents per kilowatt hour. This would correspond to a cost of about $8,838. Gasoline is, I don't know how many more times expensive gasoline is than electricity, but it's significant. It's enough to motivate a lot of drivers to switch to electric vehicles. And I have to guess that rocket fuel is far more expensive than standard gasoline. In fact, I wouldn't be surprised if the cost is easily more than 100-fold as expensive. So I'm going to guess it would cost at least $880,000 in fuel costs to get a satellite up to that orbit, if not more. Then there's the cost of manufacturing the satellite, maintaining the satellite, and so on. And by the way, a 2,000 kilogram satellite is probably a low estimate for the mass. So the next time you complain about your bill for satellite service, don't forget the tremendous cost that you can't get around. There's no violating the law of conservation of energy. It takes a significant number of joules to get these geosynchronous satellites into orbit, and there's no way around escaping the associated costs.